Good morning, all. Today I am going to teach you about IC fabrication from Unit 1. Okay, in this IC fabrication, what topics we are going to cover is the main outcome of this is how the fabrication process of linear ICs are happening, and we are going to discuss about the fundamentals of IC. In this particular slide, we are going to see about what is the definition for an IC, list the types of IC based on criteria, advantages of IC over discrete components, and various integration levels of ICs. So the contents, what is an IC, types of ICs are available, advantages of ICs over discrete components, and various integration levels. Okay, what is an IC? That is integrated circuit. Okay, so the integrated circuit, an integrated circuit is a miniature low cost electronic circuit consisting of active and passive components fabricated together on a single crystal silicon. So for example, for an IC is, so far we have done many labs like our microcontrollers, our logic gate ICs, okay, and microprocessors. So the process in our computers and mobile phones. Okay, so these are the things, right? Or the ICs are there. Okay, just a minute. Next, the active and passive components. So my transistors and diodes are all active components, and resistors and capacitors are all passive components. Okay, so our IC is made up of all our active components as well as the passive components. Next, these are the some images of our integrated circuit. This one is op-amp IC. So 741. So another, this one is LM555 IC. So timer IC. Okay, so these are all some other analog ICs, maybe in our motherboards or some other electronic PCBs. Okay, these are all ICs. Okay, so next, the history of IC. So the IC, which is also referred to as chip or a microchip, is a set of electronic circuits on a small chip of semiconductor material, normally silicon. Okay, so in a small size of substrate like this, we are having so many transistors forming a circuit. So this is called a chip. So this can be made smaller than a discrete circuit made from independent electronic components. Okay, so this looks very smaller than our discrete circuits. Okay, so ICs can be made very compact, having up to several billion transistors. Even this size of an IC will have billions of transistors. Okay, and other electronic, not only transistors and other electronic components like resistors, capacitors, inductors, and so on. Okay, so the size is very small, like a fingernail. Okay, so next, the structure of IC. Okay, so how this IC is made, how this IC is designed. Okay, these are the steps of how the IC is designed. System specification is the sense how my system should be. So specification for that particular system, that means IC. Then architectural design, functional design, circuit design, physical verification, fabrication, packaging and testing, and chip. Okay, so these are all the steps involved in designing and manufacturing an IC. So the final component is our chip. So each and every step is a very big processes. Okay, like all these steps are very big process, and each steps brings out something, some part of the IC. So the classification of ICs. The ICs are classified into, just a minute, classified into based on the application, based on fabrication techniques, based on the technology, and based on the device count. The first one is based on the application, like what kind of application the ICs are intended for, whether it is for linear application or analog application or for digital application. So this is the part we are going to study throughout this course, linear ICs. Then for based on the fabrication techniques, whether it is a monolithic IC or a hybrid IC. Monolithic in the sense, mono means one, lithic means on a single stone or rock, it's been scribed. Okay, on a single stone or rock, the ICs are what, etched. This is monolithic. So hybrid is not only single, it is kind of many monolithic ICs or kind of SoC or something like that. So many different types of technologies and different chips formed a single IC. Okay, kind of thing. Next is based on technology. What kind of technology the IC is using, whether it is a BJT, bipolar junction transistor, or a MOSFET, or say MOS like NMOS or PMOS or CMOS, and some other new technology is also available right now like FinFET, GAAFET, etc. Okay, like and based on the device count, whether it is SSI means small scale integration, medium scale, large, like large scale integration, very large scale integration, and ultra large scale integration. Right now this term VLSI, it is very famous and becomes a significant one in IC industry. So advantages of integrated circuit. So one of the main advantages is miniaturization and hence increased equipment density. It's miniaturized, and so the size of the circuit is reduced or miniaturized, so that the size of the equipment is reduced, and the density in a single or a small piece of silicon, so many transistors can be fabricated. Like previously in this site, maybe in this small size of silicon substrate, very few transistors can be fabricated. now that is historical. Now billions of transistors can be fabricated here. Then cost reduction due to batch processing. So for bulk processing, bulk manufacturing, so the cost is reduced because of bulk manufacturing. Increased system reliability due to elimination of soldered joints, improved functional performance, matched devices, increased operating speeds, and reduction in power consumption. So the power consumption is reduced. Okay, the speed increased in speed, reduction in power consumption. Okay, many devices matched with this functional performance. The performance is improved, right? And improved or increased reliability, it becomes more reliable because we have eliminated many solder joints. Okay, so these are few advantages of an integrated circuit. Next, some limitations of integrated circuits. As ICs is small in size and it is unable to dissipate large amount of power. So it cannot dissipate large amount of power since it is small size. Nowadays these issues are being overcome. It's been in the process. Increase in current may produce heat and it may destroy the device. So if there is more current, then it may destroy the device. The coils and inductors and transformers cannot be fabricated in an IC, but this is historical. So we can fabricate inductors. Okay, we can fabricate inductors in our IC. This may not be a limitation for an integrated circuit. So then generation of ICs: small scale integration, medium scale integration, large scale integration, very large scale integration, very large scale integration, wafer scale integration, nanotechnology. All these are like generation of ICs. So in large scale, small scale integration, the number of transistors are up to 10. In medium scale, it's up to 500, 10 to 500. In large scale, up to 20,000 transistors has been integrated. In VLSI, very large scale integrations, 10 lakh or a million transistor, or even more than million transistors. This ultra large scale integration, they are saying more than a million transistors. So now things are going beyond that, right? Not even million, the billions of transistors can be integrated. Okay, the next is the fabrication process of linear ICs. Okay, in this step, in this PPT, we are going to see about the steps which is involved in silicon wafer preparation. So the basic process involved in fabricating monolithic ICs. The process are silicon wafer preparation, or say substrate preparation, epitaxial growth, oxidation, photolithography, diffusion, ion implantation, isolation technique, metallization, assembly, processing, and packaging. Okay, the first one is silicon wafer preparation. So in the silicon wafer preparation, the first one is crystal growth and doping. Second one, ingot trimming and grinding, ingot slicing, wafer polishing and etching, wafer cleaning. Okay, so this is what we say as a silicon bowl. Okay, so this is pure silicon. Okay, so So this one is been ground and trimmed and grinded. Then we have to slice this. Okay, ingot slicing. We have to slice this. Then we can get a wafer. Okay, we'll show you in the coming slides. Okay, so this is a silicon bowl. And wafers are made because of slicing. Okay, so how this wafer is being made? Okay, a basic raw material silicon wafer obtained in the following steps. I am just going to tell about the steps how a silicon wafer is being obtained. The crystal growth. Okay. The step 1, the crystal growth and doping. Wafer is cut from silicon ingot bars and it's obtained from a crucible melt of pure polycrystalline silicon. Okay, so in the last week class we have seen Chalsky method. Okay, in this method we created or we made a silicon bowl, right? We made a silicon bowl, right? So that is what ingot. Okay, ingot bars. So in that, okay, wait. Okay, so last week you have seen we place a small silicon crystal in a molten silicon, then we rotate this, right? Then we lift up this bar with this pure silicon bar is been pure silicon has been created with that bar. Then we say silicon bowl. That is what Chalsky method is doing. So after doing this silicon bowl, it has been trimmed and sliced. After slicing we will get the silicon wafer. So this polycrystalline along with suitable amount of doping impurities placed in a quartz crucible. Okay, the material heated to a temperature and that is slightly excess the melting point of silicon. So the melting point of the silicon is 1420 degrees Celsius. Seed crystal will be converted into silicon ingot by freezing onto the end of the seed crystal. Okay, so in this crucible, that is crucible is kind of tank. Here a pure silicon has been placed. Here quartz, this is quartz crucible. It is with impurities and silicon, polycrystalline silicon. So when this been inserted here, okay, the seed crystal will be converted to silicon ingot by freezing, inserted and rotated. That is what I already said. Both the crystal rotated in opposite direction during the crystal pulling process in order to get circular silicon ingots. So to get a circular ingots we do like this. Yes, this is molten silicon, polysilicon, doping, introduction of seed, this crystal, very pure crystal, pure silicon. Then beginning of the crystal growth. Crystal is being grown around this seed. Then crystal pulling. Then formed crystal with residue in the melted silicon. Once all the steps are complete, these wafers are cut into many rectangular chips like this wafers, right? Then small chips is being fabricated over here and many chips are made. So on the wafer, this is a wafer, so many chips like this square things are chips. It has been circuits are etched over here on each square part, then it has been cut into small chip. Okay, so this p-type substrate, the bottom most layer that serves as the body of the substrate, upon which the complete IC is built. So P substrate or P-type substrate is the bottom of our IC substrate. So a typical P crystal is grown in the dimension of 250 mm length and 25 mm diameters as shown in the figure. Okay, it will be shown in the next slide. Silicon is preferred. The crystal is then cut by diamond saw into thin slices called wafers. Okay. These wafers are being labbed and polished to mirror finish, serve as the base of substrate in which hundreds of ICs are produced. Okay, so this is the substrate, the P-type substrate. Then over that we'll have an epitaxial layer, right? This one. Okay. Then, okay, fine. So quiz for you: which gas is used for crystal pulling in Sochalski growth in IC manufacturing? So the answer is argon.